Okay, in this video we're going to talk about writing formulas of ionic compounds. So before we get to writing formulas of ionic compounds, we have to talk about polyatomic ions. Right, so we've already talked about monatomic ions, right? Ions that involve just a single atom, right? We know that sodium, when we look at the periodic table, when it forms an ion, it likes to lose one electron and form a positive charge. Or chlorine, when it forms an ion, it likes to gain one electron and form a -1 charge. Well, not only can atoms form ions, but so can molecules. And so when a molecule gains or loses electrons, we call it a polyatomic ion. And we can pair both monatomic ions or polyatomic ions with ions of the opposite charge to form ionic compounds. And just to give you an example of a polyatomic ion, one polyatomic ion is the nitrate ion. So in this ion, it is composed of one nitrogen and 3 oxygens, and altogether this molecule gains an extra electron to give it a -1 charge. So this is a list of some common polyatomic ions, and you have to memorize these. I can't stress how important it is throughout Chem 1211 and then again in Chem 1212 that you know these polyatomic ions. I know it seems like a lot of work, it looks like there are a lot of these, but it's kind of like, you need to know the alphabet before you can read. You have to know these polyatomic ions to do a lot of the chemistry that we want to do. And so my best recommendation is to make some flashcards. Just carry these flashcards around with you, right? When you're waiting in line at the grocery store, whip out the flashcards, right, and practice your polyatomic ions. I also have created electronic flashcards through the website Quizlet, and there's a link to that on D2L in the Chapter 3 material. And when you're learning the polyatomic ions, right, so you need to know the name. And for example, for carbonate, I need to know that that is 1 carbon and 3 oxygens, and it's also vitally important that you know the charge. So you have to know that carbonate is CO3 with a 2- charge. You have to know that chlorite is ClO2 with a -1 charge, and so on. Right, and I'll point out one that's just a little bit special. All of these polyatomic ions, except for the ammonium ion, are negative. And ammonium is a common polyatomic ion that actually has a positive charge. Now, just some tips or patterns that you may notice in these polyatomic ions. Right, a lot of the ions are related to one another. So 4 that you need to know are perchlorate, chlorate, chlorite, and hypochlorite. Well, some of these patterns appear over and over again. So if you know chlorate is ClO3 minus, the same base name but ending in a different suffix. So when I go from ate to ite, we just drop the number of oxygens down 1. So chlorate is ClO3 minus, chlorite is ClO2 minus. If we put a hypo in front of the chlorite, we drop another oxygen. If we put a per in front of the chlorate, we add another oxygen. Right? And so another example that follows the same pattern. One of the polyatomic ions that you need to know is the sulfate ion. And if you know that sulfate is SO4 2-, if I then ask you what sulfite is, well, when we go from ate to ite, we drop an oxygen. Charge stays the same. So when I go from sulfate to sulfite, it's SO3 2-. So some other patterns you'll see. We have a number of different polyatomic ions where, for example, carbonate is CO3 2-, hydrogen carbonate is HCO3-. In this case, the charge does change. So we add a hydrogen, and we're really adding an H+, so the charge goes from -2 to -1. Right, same thing. If we know sulfate is SO4 2-, hydrogen sulfate is HSO4-. And so adding this hydrogen in front of the name of the polyatomic ion is another common thing that you'll see. And so if you learn these patterns, I think what you're going to find is it reduces the number that you need to know, really. And so instead of the 23 separate ones, we really only have 12 polyatomic ions that you need to know. And I think that's a little bit more manageable. All right, so writing the formulas of ionic compounds falls into sort of a general category called chemical nomenclature. Right, in chemical nomenclature are systematic rules for determining the names and formulas of chemical compounds. And so this video is specifically about writing the formulas of ionic compounds, and then we'll talk about covalent compounds and acids more. So the whole idea behind writing formulas of ionic compounds is that while it's composed of ions, the total compound has to have no charge, right? And so the charges of the positive ions have to cancel out the charges of the negative ions, and vice versa. So if we're going to make an ionic compound between sodium ions and sulfur ions, right, because sodium has a +1 charge and sulfur ions have a -2 charge, in order to combine these in a way that the compound overall is neutral, I need 2 sodiums for every 1 sulfur. And so then the formula of sodium sulfide is Na2S. All right, so obviously it's important to know the charges on that the different ions like to form. And so we've talked about this in class already, but I thought I would review it because it's so important for this material. The ions that we know the charge of. So most metals we don't, but the metals that we know the charge of are the alkali metals. We know they're +1. The alkaline earth metals, we know they're +2. And we've already talked in class, we talked about that we know aluminum, right? Aluminum is +3, right? And we can kind of see, right, when we go from 11 is +1, magnesium 12 is +2, we go to 13, aluminum is +3. Turns out there are 2 other ions that we always know the charge of. We know that zinc is +2 and silver is +1. So the way I remember, right, so the alkali metals and alkaline earth metals are kind of easy, right? First column, alkali metals +1, +2, and then there's sort of a stair step, right? 3, 2, 1. The rest of the metals, right, if we have any metals right in here, any of the metals down here, the lanthanides and actinides, they can have multiple possible charges, and so I can't tell you without being given more information what their charge is going to be. Now the nonmetals, right, and remember the dividing line between metals and nonmetals is here, right, and the metalloids are the atoms that fall on that line. All of the nonmetals, we know what charges they like to form. So the halogens, we know they like to be -1. Oxygen's family likes to be -2. Nitrogen's family, -3. Carbon likes to be -4. So it's really important to remember the atoms whose charges we know when they form ions. All right, so let's look at a couple examples now. So I want to write the formula of the ionic compound made from aluminum ions and oxide or oxygen ions. And so the way I do it is I say, okay, I write down each atom and the charge that I know it has when it's an ion. So I know that aluminum likes to be +3 and oxygen likes to be -2. The way I do it is I know that the charges have to cancel out. So the positive charges on the aluminum have to cancel out the negative charges on the oxygen. So I'm looking for the lowest common product between 3 and 2. And so I know that that's 6. So to get to 6 plus and 6 minus, I'm going to need 2 aluminums and 3 oxygens, right? Because now if I do 2 times 3, that's +6. 3 times -2 is -6. And so the +6 is going to cancel with the -6. There's another way to do it that I like to show because a lot of students like this better. So you start out the same way. Write down each ion with its charge. Right? And then what you can do is we can swap the charge of one becomes the subscript on the other one. So the 3 moves down here, the 2 moves down here, and this is really just a trick, but it works, right? That gives me Al2O3, which is the same thing that I had here. All right. The only thing we have to be careful of is the formula of ionic compound has to be the smallest whole number ratio of the subscripts. And so, just as an example, if we had lead with a +4 charge, and lead's not one of the ones that we generally know, but I'm telling you in this case, we specifically have a lead +4. If we were to combine that with oxygen, right, and I do the swap, and if I do it my way, right, I see, okay, I need 2 oxygens for every 1 lead, and that'll give me -4 and +4. So the formula should be PbO2. If you do it with the swapping, you get Pb2O4, And so you just have to remember, you've got to reduce these, right? So 2 and 4 are both divisible by 2, so we need to reduce that to PbO2. Okay, so if we look at forming a compound between potassium and nitrogen, right, I'm going to go, so potassium is K. I look at the periodic table, it's an alkali metal, so it has a +1 charge. Nitrogen, when it's an ion, is going to have a -3 charge, so the 1 and the 3, and I get K3N. Now, so far we've just been doing monatomic ions. Phosphate is one of the polyatomic ions that we need to know. And so phosphate is PO43-. And so when I'm writing the formula, I've got to keep the PO4 together. I can't break up the PO4. Right? And I'm going to need to balance the +2 that the calcium ion has with the -3 on the phosphate. Right? And so with my method, I would say, okay, I've got 2 and 3, so I'm going to need to make this +6 and -6. And so to make calcium +6, I'm going to need 3 of them. So I'm going to have Ca3. I'm going to need 2 phosphates to get to -6. And so because I've got to keep the phosphates all together, the way I do that with the parentheses. So if I need more than one polyatomic ion, I put the whole polyatomic ion in parentheses, and then I need 2 of those phosphates, and so the 2 goes outside the parentheses. And the 2 applies to the whole phosphate. It applies to the phosphorus and the 4 oxygens. And it also applies to the charge, right? So I have 2 PO43-, that's going to be -6. I have 3 + 2 calciums, that's +6. So +6, add it to -6, and I get 0. Right? You can do the same thing with the swapping. Right? I would say Ca2+, right? The 3 from the phosphate becomes the new subscript for the calcium, and the 2 from the calcium becomes a subscript on the whole phosphate. And so again, we get Ca3 PO4 2. Okay, so this is a little bit of a rehash. We've already talked about, we know the charges on alkali metals and alkaline earth metals when they're ions, and when aluminum, zinc, and silver are ions, we also know their charges. Every other metal can have multiple possible charges. And so in order to write the formula, we have to know what the charge is. And so basically somebody has to tell us. If they ask us to write the formula, they've got to tell us the charge. And so in written form, we do that with Roman numerals. And so, for example, if I have iron with a +3 charge, I would tell you that I would write it as iron with a Roman numeral 3, and then in words I would say we have iron 3. Or if uranium has a +6 charge, now I would write that as uranium 6 in Roman numerals. All right, so my last slide here, let's write the formulas of these ionic compounds formed from the following ions, right? And because these are metals that can have multiple possible charges, in each case, they had to tell me what the charge on that metal is. So the number in Roman numerals is the charge on that metal. So if I want to write the formula between iron 3 and sulfur, I say, okay, I've got Fe3+. Sulfur is a nonmetal, so I know I can go to the periodic table, and I know that sulfur is -2. So we're going to have Fe2S3. Right, another example, so if we have lead 2, so that's lead with a +2 charge, and then you need to know the polyatomic ions, but I've given you the formula here because I'm guessing you don't have them memorized quite yet. The nitrate ion is NO3-, right? So I'm going to need 1 lead and 2 nitrates. And so it's going to be Pb, put the nitrate in parentheses, and there's 2 of them. All right, and then lastly we have nickel 4 and chlorine. So nickel 4, chlorine is going to be -1, so we're going to have NiCl4.